Now, if you think about the mechanism, you can think about a few situations. You could imagine that you have an oxidative addition to form a uranium-5 hydroxide hydride. This uranium-5 hydroxide hydride would then eliminate H radicals to form the uranium-4 hydroxide that we isolate. You could also imagine that you have simple homolytic cleavage that forms the uranium-4 hydroxide right away and H dot. Or you could think that uranium just behaves as a heavy alkaline metal where you actually put it in water and you produce hydrogen and base. Now, the thing is, the catalyst does not produce H dot. It doesn't produce radicals because a catalyst runs forever and ever and ever. There's no decomposition seen. And that suggests that we don't have H dots. So Dominic, my student, he suggested that why don't we propose that we have an oxidative addition similar to the mechanism proposed by Chris Cheng and Jeff Long. And now from this uranium-5 hydroxide hydride, we eliminate dihydrogen and generate a uranium-5 oxo species. Now that mechanism doesn't involve radicals, but this mechanism also doesn't give us the uranium-4 hydroxide that we have isolated. And so Dominic continues and says, well, and what we then see is subsequent comproportionation, where a uranium-5 oxo species comproportionates with a uranium-3 aquo species to give you two equivalents of uranium-4 hydroxide. And I said, well, Dominic, this is clever, but this is a very, very bold statement because this oxidative addition here from uranium-3 to uranium-5 is very unlikely because not very often seen. And this comproportionation I've never heard of in uranium chemistry. And so we asked Laurent Marron to help us and compute the reaction profile, and the reaction profile seems quite reasonable. You add water to the uranium-3 species, then you put the water in the equatorial plane, you have this transition state. This transition state is confirmed by a molecular structure where water actually coordinates to neodymium, like a derivative of our compound. And we also see that then in the water-splitting transition state B, as shown here, we have one electron that comes from the uranium center, another electron that comes from the arene to actually accomplish the two-electron oxidative addition to give the hydroxide hydride. This hydroxide hydride then forms the dihydrogen is eliminated and gives the uranium-5 oxo. This uranium-5 oxo is an immediate that we never see because the uranium-5 oxo will then immediately engage in comproportionation to give the uranium-4 hydroxide. Now this is computation. I do appreciate Laurent's contribution to our chemistry, but I also believe they can pretty much compute everything. And so we needed to look further into the mechanism. And so we independently synthesized the uranium-5 oxo species. And when we look at the EPR spectrum, we noticed a standard uranium-5 EPR spectrum. But Dominic is a very careful student, and he also noticed this little signal here. And typically, you would probably cut the EPR spectrum right there so the supervisor doesn't see that there is an impurity. But Dominic actually said, well, let's see what this is. And so at 7 Kelvin, you see a standard uranium-5 spectrum, but at 90 Kelvin, this spectrum now becomes dominant, and we have a spectrum centered at 1.997 with a line width that is very characteristic for an organic radical, and that's exactly what it is. I mean, it's not a uranium-5 species, it's a species that has actually radical character, a charge-separated state within the uranium oxo species, and that's pretty much nails it. And so the concerted two-electron reaction that is crucial in transition metal catalysis, but barely observed in uranium chemistry, and that comes along due to the fact that the arenes and the aryl oxide is involved. Now, as I said to you, I'm a chemist and I'm a trained chemist. I want to see chemical proof of a mechanism. And probably the most elegant reaction that Dominic carried out is this reaction shown here. So the comproponation is actually what I doubted. And so he said, well, we can isolate the uranium-3 species. We can independently synthesize and isolate the uranium-5 oxo species. This is the comproponation if water is present, and this reaction gives you two equivalents of uranium-4 hydroxide and nothing else. And you can see that this reaction is just very, very clean. So uranium-5, uranium-3, one equivalent of water will give you the hydroxide. This is the comproponation. Okay. Now, the overpotential at 1.3 volt is still a significant overpotential, and I'm not going and staying here and stating that this catalyst will save the planet. No, it will not save the planet, but we wanted to address this overpotential, and of course, when you are working at the bottom of the periodic table, especially when you're working in Germany, there is no way I could do thorium chemistry or even plutonium chemistry. And so Dominic meets Bill Evans, a very prominent F-element chemist in the United States at UC Irvine, and suggested that we are looking at the lanthanides. And so together with Bill's student, we synthesized all of the lanthanide complexes and could show that every single lanthanide complex is actually electrocatalytically active. So you don't have to do uranium, you can also do lanthanides if you fear the radioactivity of uranium, for instance, and you can see that you can fine-tune the potentials quite nicely. So for instance, samarium has a lower overpotential than uranium has, and neodymium has a higher overpotential than uranium. Eventually, you're losing driving force, and the reaction no longer proceeds. The mechanism is different. I showed you for the actinides, we started with low-valent uranium-3 and then get to the uranium-4 hydroxide that is electrochemically regenerated or regenerating the catalyst. In lanthanide chemistry, we need to do the reduction first to get to the divalent state, and then the divalent state will produce hydrogen from water. Okay.